Hi, my name is Ryan Card. My specialty is in probability theory. That means I like modeling things that have uncertain outcomes. Today, I wanted to tell you about this. I'm excited to tell you about what's called the Ross-Littlewood Paradox. Let's get right to it. Okay. All right. So in this problem, I have an infinitely large urn and infinitely many balls that's numbered 1, 2, 3, 4, and so on. What we're going to be doing is we're going to be taking some of these balls, putting it into the urn, and then removing it from the urn and then putting it back in and so forth. We're gonna do this in a very particular way. In fact, we will perform infinitely many tasks in a finite amount of time. So you can kind of imagine we're 1 minute from noon. That's 11:59, and then we'll take 30 seconds to do our first task. And after we're done with our step one, we're gonna do 15 seconds to do our second step, and then uh, one 1/8 of a minute, and then 1/16 of a minute, and so on. So we're gonna try to accomplish infinitely many things uh, before noon, and once it hits noon, we're gonna figure out what's gonna be inside the urn at that time. Okay, so here's our first scenario. What we're gonna do is we're gonna put in balls 1 through 10 and then remove the smallest numbered ball. So we're gonna take 1 through 10 and then you remove the first one. So we have 2 through 10 inside of the urn. Then we're gonna put in balls 11 through 20 and then we remove the smallest number ball that's still in the urn. So in that case, it would be 2 because 1 is already removed. And then we repeat this process. We're going to do this infinitely many times. Okay. So let's see. I'm going to put in balls 1, 2, 3, all the way through 10. Once I do that, I'm going to remove the smallest number of balls. So I'm going to remove 1. That's step 1. And then on step 2, I'm going to put in balls 11 through 20. And then remove the smallest ball. That's number 2. And then that's step 2. And this is the step 3, and so on. So I hope you can imagine what would happen. Okay. So try to see for yourself, what do you think would happen at noon when you repeated this process infinitely many times before noon. So one thing that you might have noticed is that the bowl numbered n is removed on the nth step of this process. So bowl number 1 was removed on the first step, bowl number 2 was removed on the second step, and bowl number 17 will be removed on the 17th step of this process. So every ball, 5 bajillion, is going to be removed on the 5 bajillionth step of this process. So every ball is eventually removed from this urn. So although it may sound strange, no ball will be inside of the urn at noon. Now, this is already paradoxical, but if you've dealt with like things with infinite sets before, this might not be too surprising, even though it feels like there's more and more balls in the urn. As time goes on, there'll be nothing left at the end. Okay, let's do this with a different setup. Okay. Oh, so I wrote down what this means in terms of sets, but you don't have to pay too much attention to that. Okay, so let's do second scenario. Okay, so this time we're going to do a similar setup. We're going to put in balls 1 through 10, and then this time remove the largest number ball. So ball number 10. On the next step, we put in balls 11 through 20, and then we remove the largest number ball, and then repeat this process. So try to imagine what will happen in this case. Okay. All right, so let's put in ball 1 through 10. And the largest ball is number 10, so we remove that. On the second step, we put in 11 through 20. Largest is 20 there, and so on. Now what would happen if we repeated this infinitely many times and look in the urn at noon and see what's in it? You might have noticed that every time you put in sets of 10, the largest number one is the last ball you put in. That's a number that's multiple of 10. That's the one you're gonna remove at each step. Okay. So what's left after infinitely many steps would be every other ball. So every balls numbered that are multiple of 10 will be removed on the nth step of this process. What you'll have is all the balls, all the infinitely many balls that doesn't have a 0 on the ones digit. Right? So any ball that's not multiple 10 will be left in there. Okay, so we've had two very similar processes where we put in numbers 1 through 10 each step at a time, and we remove a very particular one. And how we do this actually affects what's left in the urn at noon. Okay, this is already paradoxical enough. So this is the Littlewood's paradox. But now let's put in probability into it. So here's scenario number 3. Okay, we're gonna do something similar. We're gonna put in 10 balls, but after putting in 10 balls, what we're gonna do is we're gonna randomly choose the one we're gonna take out at each step, and then repeat that process, right? So what do you think will be left inside of the urn? What would it look like at noon when you peeked in after doing this infinitely many times? Would it be empty like it was the first case where we were removing the smallest ball? Or would it be infinitely many balls with some being left over in there? Or is there going to be finitely many balls? That's a weird situation, but what do you think will happen? Let's work it out. All right. So yeah. Okay. So I think this is not at all obvious what will happen. So we'll do this in steps. The first step is to analyze what would happen to one particular ball. So let's try to see what would the probability for one surviving this process infinitely many times. Okay. So we're gonna say the event that the number one ball survives n steps of this process, that would be event Sn. Okay, so the probability that the one ball survives the first step is that just not be drawn the first time. So there's going to be 10 balls, and one is just one particular ball out of the 10. So the probability of surviving the first draw would be 9 out of 10, right? That's reasonable. After surviving the first draw, the way to survive the second draw would be after putting in 10 more balls, there should be 19 balls left inside of the urn. And if one wasn't drawn on the first step, then the probability that it survives the second draw is 18 out of 19, because it's only one ball out of that 19. So that's S2, probability of surviving 2 steps of this process. And I hope you kind of got the pattern from this. So the third step, we multiply by the probability of surviving each of the first 2 draws. There's a typo here. That should be 19. After putting in 10 more balls, after drawing 2, you should have 28 in the urn. And the probability of surviving the third draw would be 27 out of 28, and so on. So here's the pattern. Right? We multiply fractions, and on the nth step, you multiply by the fraction 9n divided by 9n plus 1, right? Because after each step, you gain 9 more balls in the process, and there's one extra one for the last step because you haven't drawn the ball yet. Okay. And this notation you might have seen before, but if you've taken a calculus course or a statistics course, you probably have seen a summation notation. This means add up expressions that look like this. If we are multiplying things, we use Greek capital letter pi, and this is the product notation. Okay, so the question is, okay, so this is the probability that it survives n steps. What happens at noon? So what happens as we take this n to infinity? What happens to the probability of survival? This is what we want to compute. Okay. And my claim is that the probability goes to 0. So we'll do this, but I think it's a little bit easier to analyze the reciprocal of this expression. So flip this fraction upside down, and this expression going to 0 is equivalent to showing the reciprocal, the product of the reciprocals, is going to infinity, right? So these are all positive numbers. That's if they're going to 0, then they're becoming smaller and smaller positive number. Reciprocal of something 1 divided by something that's going to small will blow up to infinity. And if you look at the reciprocal expression here, you could divide each of the 2 terms on the top by 9k and rewrite the expression in a little bit simpler way. So 1 plus 1 over 9k is what you're multiplying each time. That's a little bit easier to work with. All right, so let's see this expression. So if we're multiplying any of these things together, this is kind of written out as a product of n different things. And let's multiply everything out, right? So there's a term where you can get, if you multiply all the ones together, that would be 1. Other terms you can get would be multiplying 1/9 times all the ones in the other factors, and that would give you 1/9. Or you could do the similar thing for all the multiples 9 fractions. So 1 times 1/18 times all the ones will give you 1/18, and so on up until 1 over 9n. Now there are other other terms that you can get when you multiply this out. You haven't foiled everything out. For example, we haven't looked at the terms where all the fractions are multiplied together. Let's just throw all those away. Those terms are positive, so if we drop it, we'll get a slightly smaller expression. But this is enough for us to analyze what's going to happen to this product. Okay. Leaving one alone, all of the other fractions that we've added, those are all multiples of 9. So we could factor out 1/9, and this is what we have left over, 1 plus 1/2 plus 1/3, and so on up until 1/n. If you've taken Calc 3 course, maybe you recognize this as a harmonic series, right? So this is a finite harmonic series, but as n goes to infinity, this will blow up to infinity, right? So there you go. So let's kind of review what we did so far. We show that this product blows up to infinity, which means it's reciprocal. This product will go towards 0, right? And remember that expression is the probability that the ball numbered 1 survives up until noon, infinitely many draws of this process. Okay. So the probability that the 1 is left in the urn after infinitely many steps is 0. Okay. Now let's figure out if there's going to be any ball left in the urn. So we have to give it some names. So let's say B sub k is an event that the ball number k is left in the urn after infinitely many of those process. Okay. So the probability that any ball left after that infinite process, well, you could see the event that any ball is left is same as the combined process of combined event of events that a particular ball is left after infinitely many draws. And you can show that the probability of these type of combined events are at most the sum of the probability of individual events. And those individual events are very similar to the case of the survivability of ball number 1. They're not exactly the same, but you could do a certain type of similar type of analysis to show that each of those probability does go to 0. So the probability is going to be sum of 0 plus 0 plus 0 plus 0 and so on. The probability that any ball survives this infinite drawing process is 0. Nothing is left over at the end of this process. Pretty cool, right? I really like this problem. Okay, so is this problem complete? And I think, well, this is the Ross-Littlewood paradox that's as stated, but I think you could do little twists to these problems. And in fact, it turns out that the answer that there's no balls left could be changed if you change the process a little bit. For example, if you start adding maybe more and more balls to the urn. So maybe on the first step, you add 10. On the next step, you add 11. And next step, you add 12, and so on. And see if that changes the result. And I don't want to spoil the answer yet because I want you to tackle this capstone project possibly. But the answer does change. And I want you to come up with a way to tell when there will be balls left and when there isn't. Another question you might have at this point is like, well, maybe this sounds cool, but is this related to real life whatsoever? Because all this process with infinitely many large, infinitely many balls and infinitely large urn and doing infinitely many things in a finite time, all this sounds absolutely abstracted and bizarre. But I think actually being able to compute these things and prove these things are relevant. For example, uh, maybe you have a situation where you get more emails than you can reply in a particular day. Maybe you get 100 emails and you can reply 20 per day with a given amount of time. Maybe you'll like prioritize certain types of emails, but there are some still random emails that you can get to. So if you start replying those emails like from in the order you received, then you'll get super delayed in your emails, and none of what you're replying is going to be current anymore. Or if you answer the emails in the reverse ordering, the newest, if you answer the newest email first, then some of those emails will never be answered. Or maybe your strategy could be answer some important emails and then randomly choose some leftover emails from the inbox that you haven't replied to. And this will give you the answer that if you can get to all the emails eventually or not. And the answer, now we know, is yes, or um, maybe no if you're getting more and more emails. Another more practical situation is that maybe if you're programming some data stream processing algorithm. So we live in a big data society where sometimes you have some data source where you can't download all the data because it's too much to download and process. So if you're working with like a Twitter feed or a Facebook feed or this stream of data that you can't possibly process them all, but you could pick up random samples from the data stream. And depending on how you deal with those random samples, you could answer theoretical questions about like, hey, if I randomly choose this from this pool of ever-growing YouTube videos, would I eventually get to all the YouTube videos? And you could answer questions like that with analyzing processes like this. So I think it is kind of relevant. You just have to recast the problem into a situation like that, into a situation where you could do less than all the tasks that are given to you. Okay. All right. So here's if you think that was interesting, this is a possible capstone project. You can learn basic probability theory and learn theorems that helps us decide that if this infinite process, random process, would happen finitely many times, or if something happens infinitely many times. There are class of theorems that helps us decide when it happens and when it doesn't. And I want you to translate that criterion into something where, okay, if you're getting this much balls into the urn at each step, would you be able to classify the cases where there will be no balls left or there's infinitely many balls left? I think that would be an interesting capstone project you can tackle. Okay. And here are some references for this particular paradox, Ross-Littlewood Paradox. Okay, that's it for this video. I'm looking forward to talking to some of you soon.